The Mathematical Analysis of Logic, being an essay towards a calculus of deductive reasoning, by George Boole. Part 2. Of Syllogisms. A syllogism consists of 3 propositions, the last of which, called the conclusion, is a logical consequence of the 2 former, called the premises, e.g., premises. All uppercase Y's are uppercase X's, all uppercase Z's are uppercase Y's. Conclusion, all uppercase Z's are uppercase X's. Every syllogism has 3 and only 3 terms, whereof that which is the subject of the conclusion is called the minor term, the predicate of the conclusion the major term, and the remaining term common to both premises the middle term. Thus in the above formula, uppercase Z is the minor term, uppercase X the major term, uppercase Y the middle term. The figure of a syllogism consists in the situation of the middle term with respect to the terms of the conclusion. The varieties of figure are exhibited in the annexed scheme. Column 1. First fig, uppercase Y, uppercase X, uppercase Z, uppercase Y, uppercase Z, uppercase X. Second column. Second fig, uppercase X, uppercase Y, uppercase Z, uppercase Y, uppercase Z, uppercase X. Third column. Third fig, uppercase Y, uppercase X, uppercase Y, uppercase Z, uppercase Z, uppercase X. Column 4. Fourth fig, uppercase X, uppercase Y, uppercase Y, uppercase Z, uppercase Z, uppercase X. When we designate the 3 propositions of a syllogism by their usual symbols, A, E, I, O, and in their actual order, we are said to determine the mood of the syllogism. Thus the syllogism given above, by way of illustration, belongs to the mood A in the first figure. The moods of all syllogisms commonly received as valid are represented by the vowels in the following mnemonic verses. Fig 1, Barbara, Silurant, Darii, Ferio K Prioris. Fig 2, Caesar, Camestris, Festino, Barocco Secundae. Fig 3, Tertia Darapti, Disamis, Datisi, Felapton, Boccardo, Feriso, Habet, Quata in super adit. Fig 4, Bramantip, Camenis, Dimaris, Fesapo, Frasison. The equation by which we express any proposition concerning the classes uppercase X and uppercase Y is an equation between the symbols lowercase x and lowercase y. And the equation by which we express any proposition concerning the classes uppercase Y and uppercase Z is an equation between the symbols lowercase y and lowercase z. If from 2 such equations we eliminate lowercase y, the result, if it do not vanish, will be an equation between lowercase x and lowercase z, and will be interpretable into a proposition concerning the classes uppercase X and uppercase Z, and it will then constitute the 3rd member or conclusion of a syllogism, of which the 2 given propositions are the premises. The result of the elimination of lowercase y from the equations all lowercase a y plus b equals 0, a prime y plus b prime equals 0, 14, is the equation all lowercase a b prime minus a prime b equals 0, 15. Now the equations of propositions being of the first order with reference to each of the variables involved, all the cases of elimination which we shall have to consider will be reducible to the above case, the constants lowercase a, lowercase b, lowercase a prime, lowercase b prime, being replaced by functions of lowercase x, lowercase z, and the auxiliary symbol lowercase v. As to the choice of equations for the expression of our premises, the only restriction is that the equations must not both be of the form lowercase a y equals 0, for in such cases elimination would be impossible. When both equations are of this form, it is necessary to solve one of them, and it is indifferent which we choose for this purpose. If that we select is of the form lowercase xy equals 0, its solution is all lowercase y equals v open brackets 1 minus x close brackets 16. If of the form open brackets 1 minus x close brackets y equals 0, the solution will be all lowercase y equals vx 17, and these are the only cases which can arise. The reason of this exception will appear in the sequel. For the sake of uniformity, we shall, in the expression of particular propositions, confine ourselves to the form all lowercase vx equals vy, all uppercase some x's are y's, all lowercase vx equals v open brackets 1 minus y close brackets, all uppercase some x's are not y's. These have a closer analogy with 16 and 17 than the other forms which might be used. Between the forms about to be developed and the Aristotelian canons, some points of difference will occasionally be observed, of which it may be proper to forewarn the reader. To the right understanding of these, it is proper to remark that the essential structure of a syllogism is, in some measure, arbitrary. Supposing the order of the premises to be fixed, and the distinction of the major and the minor term to be thereby determined, it is purely a matter of choice which of the two shall have precedence in the conclusion. Logicians have settled this question in favour of the minor term, but it is clear that this is a convention. Had it been agreed that the major term should have the first place in the conclusion, a logical scheme might have been constructed, less convenient in some cases than the existing one, but superior in others. What is lost in Barbara, it would gain in Brumantip. Convenience is perhaps in favour of the adopted arrangement. Footnote. The contrary view was maintained by Hobbes. The question is very fairly discussed in Hallam's Introduction to the Literature of Europe, Volume 3, page 309. In the rhetorical use of syllogism, the advantage appears to rest with the rejected form. End of footnote. But it is to be remembered that it is merely an arrangement. Now the method we shall exhibit, not having reference to one scheme of arrangement more than to another, will always give the more general conclusion, regard being paid only to its abstract lawfulness, considered as a result of pure reasoning. And therefore we shall sometimes have presented to us the spectacle of conclusions which a logician would pronounce informal, but never of such as a reasoning being would account false. The Aristotelian canons, however, beside restricting the order of the terms of a conclusion, limit their nature also, and this limitation is of more consequence than the former. We may, by a change of figure, replace the particular conclusion of Bramantip by the general conclusion of Barbara, but we cannot thus reduce to rule such inferences as, all uppercase, some not x's are not y's. Yet there are cases in which such inferences may lawfully be drawn, and in unrestricted argument they are of frequent occurrence. Now if an inference of this, or of any other kind, is lawful in itself, it will be exhibited in the results of our method. We may, by restricting the canon of interpretation, confine our expressed results within the limits of the scholastic logic, but this would only be to restrict ourselves to the use of a part of the conclusions to which our analysis entitles us. The classification we shall adopt will be purely mathematical, and we shall afterwards consider the logical arrangement to which it corresponds. It will be sufficient for reference to name the premises and the figure in which they are found. Class first, forms in which lowercase v does not enter. Those which admit of an inference are AA, EA, Fig 1, AE, EA, Fig 2, AA, AE, Fig 4. Example AA, Fig 1, and by mutation of premises, change of order, AA, Fig 4. All uppercase, all y's are x's, all lowercase, y open brackets 1 minus x close brackets equals 0, or open brackets 1 minus x close brackets y equals 0. All uppercase, all z's are y's, all lowercase, z open brackets 1 minus y close brackets equals 0, or zy minus z equals 0. Eliminating lowercase y by 13, we have all lowercase, z open brackets 1 minus x equals 0. Therefore, all uppercase, all z's are x's. A convenient mode of effecting the elimination is to write the equation of the premises so that lowercase y shall appear only as a factor of one member in the first equation, and only as a factor of the opposite member in the second equation, and then to multiply the equations, omitting the lowercase y. This method we shall adopt. Example AE, Fig 2, and by mutation of premises, EA, Fig 2. All uppercase, all x's are y's, all lowercase, x, open brackets 1 minus y, close brackets, equals 0, or x equals xy. All uppercase, no z's are y's, all lowercase, zy equals 0. Zy equals 0 over zx equals 0, therefore no z's are x's. The only case in which there is no inference is AA Fig 2. All uppercase, all x's are y's, all lowercase, x, open brackets 1 minus y, close brackets, equals 0, x equals xy. All uppercase, all z's are y's, all lowercase, z, open brackets 1 minus y, close brackets, equals 0, zy equals z, over xz equals xz, therefore 0 equals 0. Class second, where lowercase v is introduced by the solution of an equation. The lawful cases directly or indirectly determinable by the Aristotelian rules are AE, Fig 1, AA, AE, EA, Fig 3, EA, Fig 1. Footnote. We say directly or indirectly mutation or conversion of premises being in some instances required. Thus, AE, Fig. 1, is resolvable by Fisapo, Fig. 4, or by Ferriot, Fig. 1. Aristotle and his followers rejected the fourth figure as only a modification of the first, but this being a mere question of form, either scheme may be termed Aristotelian. End of footnote. Example AE, Fig. 1, and by mutation of premises, EA, Fig. 4, all uppercase, all y's are x's, all lowercase, y, open brackets, 1 minus x, close brackets, equals 0, y equals vx, a. All uppercase, no z's are y's, all lowercase, zy equals 0, 0 equals zy, over 0 equals vzx. Therefore, all uppercase, some x's are not z's. The reason why we cannot interpret vzx equals 0 into some uppercase z's are not uppercase x's is that by the very terms of the first equation A, the interpretation of Vx is fixed. As some uppercase x's, V is regarded as the representation of a sum only with reference to the class uppercase X. For the reason of our employing a solution of one of the primitive equations, see the remarks on 16 and 17. Had we solved the equation instead of the first, we should have had, open brackets, 1 minus x, close brackets, y equals 0. V, open brackets, 1 minus z, close brackets, equals y, a. V, open brackets, 1 minus z, close brackets, open brackets, 1 minus x, close brackets, equals 0, b. Therefore, all uppercase, some not z's are x's. Here it is to be observed that the second equation A fixes the meaning of lowercase v, open brackets, 1 minus z, close brackets, as some not uppercase z's. The full meaning of the result B is that all the not z's which are found in the class uppercase y are found in the class uppercase x, and it is evident that this could not have been expressed in any other way. Example 2, AA, Fig. 3. All uppercase, all y's are x's, all lowercase, y, open brackets, 1 minus x, close brackets, equals 0, y equals vx. All uppercase, all y's are z's, all lowercase, y, open brackets, 1 minus z, close brackets, equals 0. 0 equals y, open brackets, 1 minus z, close brackets, over 0 equals vx, open brackets, 1 minus z, close brackets. Therefore, all uppercase, some x's are z's. Had we solved the second equation, we should have had, as our result, some uppercase z's are uppercase x's. The form of the final equation particularizes what uppercase x's or what uppercase z's are referred to, and this remark is general. The following, EE, Fig. 1, and by mutation EE, Fig. 4, is an example of a lawful case not determinable by the Aristotelian rules. All uppercase, no y's are x's, all lowercase, xy equals 0, 0 equals xy. All uppercase, no z's are y's, all lowercase, zy equals 0, y equals v, open brackets, 1 minus z, close brackets, over 0 equals v, open brackets, 1 minus z, close brackets, x. Therefore, all uppercase, some not z's are not x's. Class third. When lowercase v is met with in one of the equations but not introduced by solution, the lawful cases determinable directly or indirectly by the Aristotelian rules are ai, ei, fig 1, ao, ei, oa, ie, fig 2, ai, ao, ei, eo, ia, ie, oa, oe, fig 3, ia, ie, fig 4. Those not so determinable are oe, fig 1, eo, fig 4. The cases in which no inference is possible are ao, eo, ia, ie, oa, fig 1, ai, eo, ia, oe, fig 2, oa, oe, ia, ei, ao, fig 4. Example 1, ai, fig 1, and by mutation, ia, fig 4. All uppercase, all y's are x's, all lowercase, y, open brackets, 1 minus x, close brackets, equals 0. All uppercase, some z's are y's, all lowercase, vz equals vy. Vz, open brackets, 1 minus x, close brackets, equals 0. Therefore, all uppercase, some z's are not x's. The interpretation of lowercase vz as some uppercase z's is implied. It will be observed in the equation all lowercase vz equals v, open brackets, 1 minus y, close brackets, considered as representing the proposition some uppercase z's are not uppercase y's. The cases not determinable by the Aristotelian rules are oe, fig 1, and by mutation, eo, fig 4. All uppercase, some y's are not x's. All lowercase, vy equals v, open brackets, 1 minus x, close brackets. All uppercase, no z's are y's. All lowercase, 0 equals zy. 0 equals v, open brackets, 1 minus x, close brackets, z. Therefore, some not x's are not z's. The equation of the first premise here permits us to interpret lowercase v, open brackets, 1 minus x, close brackets, but it does not enable us to interpret lowercase vz. Of cases in which no inference is possible, we take as examples ao, fig 1, and by mutation, oa, fig 4. All uppercase, all y's are x's. All lowercase, y, open brackets, 1 minus x, close brackets, equals 0. Y, open brackets, 1 minus x, close brackets, equals 0. All uppercase, some z's are not y's. All lowercase, vz equals v, open brackets, 1 minus y, close brackets, a. V, open brackets, 1 minus z, close brackets, equals vy. V, open brackets, 1 minus z, close brackets, open brackets, 1 minus x, equals 0. B, 0 equals 0, since the auxiliary equation in this case is v, open brackets, 1 minus z, equals 0. Practically, it is not necessary to perform this reduction, but it is satisfactory to do so. The equation A, it is seen, defines lowercase vz as some uppercase z's, but it does not define lowercase v open brackets 1 minus z close brackets, so that we might stop at the result of elimination, B, and content ourselves with saying that it is not interpretable into a relation between the classes uppercase X and uppercase Z. Take as a second example AI fig 2, and by mutation IA fig 2, all uppercase, all X's are Y's, all lowercase, X open brackets 1 minus Y close brackets equals 0, all lowercase, X equals XY, all uppercase, some Z's are Y's, all lowercase, VZ equals VY, VY equals VX, VX equals VXZ, V open brackets 1 minus Z close brackets X equals 0, 0 equals 0. The auxiliary equation in this case being lowercase v open brackets 1 minus Z close brackets equals 0. Indeed, in every case in this class in which no inference is possible, the result of elimination is reducible to the form 0 equals 0. Examples therefore need not be multiplied. Case fourth, when lowercase v enters into both equations. No inference is possible in any case, but there exists a distinction among the unlawful cases which is peculiar to this class. The two divisions are, first, when the result of elimination is reducible by the auxiliary equations to the form 0 equals 0. The cases are II, OI, fig 1, II, OO, fig 2, II, IO, OI, OO, fig 3, II, IO, fig 4. Second, when the result of elimination is not reducible by the auxiliary equations to the form 0 equals 0. The cases are IO, OO, fig 4, IO, OI, fig 2, OI, OO, fig 4. Let us take as an example of the former case, II, fig 3. All uppercase, some X's are Y's, all lowercase, Vx equals Vy, Vx equals Vy, all uppercase, some Z's are Y's, all lowercase, V prime Z equals V prime Y, V prime Y equals V prime Z, V prime X equals V prime Z.